Welcome, everyone, to this week's colloquium. My name is Jesse Thaler, and I'm one of the general members here at the Aspen Center for Physics. And this year, one of my responsibilities was to serve on the admissions committee for the center, so it's a particular thrill to see all those entries in the ACP database turn into real in-person physicists. For some of you, this is your first time experiencing the magic of Aspen summer workshops, where you can actually get some work done, except for this 1 hour where you are required be inspired by our colloquium speaker today. Our first speaker for the summer 2024 colloquium series is Feryal Özel. Feryal is an astrophysicist who is particularly interested in studying the extreme environments of compact objects like neutron stars, magnetars, and black holes. So, for example, she's worked with the NICER experiment on the International Space Station to glean information about the interior composition of neutron stars. Relevant to the colloquium today, Feryal was a founding member of the Event Horizon Telescope collaboration, which, if you remember, in April 2019, released an astonishing image of the supermassive black hole at the heart of the M87 galaxy. But closer to our neck of the woods, Feryal led the announcement of the first image of the black hole at the center of our own Milky Way, which you're going to learn more about today. Feryal received her PhD from Harvard, after which she was a NASA Hubble Fellow at the Institute for Advanced Study. For most of her faculty career, she was at the University of Arizona, but 2 years ago, she started a new adventure as chair of the School of Physics at Georgia Tech. So, Feryal, we're thrilled that you have at least temporarily escaped the black hole of academic leadership to give today's colloquium. Please join me in welcoming Feryal Özel.
Trust me, I am also truly delighted to escape that a black hole of academic leadership and be with all of you here this week and next week and lead off the colloquium series. My title is Understanding Black Holes Through Imaging, but as you will see throughout the talk, it is mostly a talk about the theory of black hole environments and how our computational and theoretical models of those environments have helped the imaging efforts. They actually shaped the imaging efforts. They helped us interpret the data that we've seen, and they actually also made us or helped us make the images better. I'm hoping at least a small part of the talk will be of interest to both workshops that are happening here this week. And with that, I'm just going to spend a couple of slides motivating why we study black holes. I know physicists of all flavors are here in the audience. So from an astronomy point of view, one of the reasons we study black holes is because, first of all, they're everywhere. And second of all, the more we observe them, the more we understand that they have shaped processes that happen in the universe. They have helped shape galaxies. There is one at the center of every galaxy that we look at, a supermassive black hole, in addition to the small scale what we call the solar mass size black holes that are ubiquitous throughout galaxies. So one thing that I would like to do with this slide also is show you the range of scales that we need to probe when we say we study black holes. Anything from the galaxy scales themselves, 100 kiloparsecs for this type of galaxy, to the scale at which black holes get their gas from nearby stars and clouds, heating radius at 100 parsecs, to the black hole accretion disk scale, where this gas loses angular momentum and makes its way to the black hole, to the event horizon, which is mostly the topic of the talk today, at 10 to the minus 4 parsecs, to the small scale plasma simulations that we've already discussed this week in the Cosmic Ray workshop, where we try to understand the kinetic processes in plasmas at 10 to the minus 11 parsecs. So you can see from 100 kiloparsecs to 10 to the minus 11 parsecs, this is a huge challenge in terms of understanding the role of black holes in the universe. From a physics point of view, black holes are also very interesting. First of all, they are singularities, and anytime there's a singularity in physics, there is room for discovery. So one of the reasons I got into this, and a lot of my colleagues got into this, is to try and understand whether black holes actually behave the way that is predicted by the theory of general relativity when we probe them at scales that are close to their event horizon. So what is the event horizon? Even more importantly, what are some interesting scales around black holes? This is a cartoon from the work in the 70s. How if you hold a flashlight, there is going to be a special radius called the photon orbit that is actually going to be lit up. And interior of that is going to be the place where gravitational lensing is so strong that there is not going to be any light escaping from it. So if I now show you this animation here, for a Schwarzschild black hole, horizon is at 2 gravitational units, which we define as gm over c squared. That special photon orbit is at 3 gm over c squared. And again, we look at parallel rays coming from infinity. The lensing that they experience, that bending that they experience around the black hole is such that all of the parallel rays within this special radius that we call the shadow radius, square root of 27 gm over c squared, is going to disappear from view. So what we expect to see in this idealized image is literally a black hole at the center, surrounded by a bright ring, where photons actually can make multiple paths around the black hole. And because of that, it's going to be extra bright. So this is one of those little interesting things about black holes. So this is for a Schwarzschild black hole. The size of the shadow has a small dependence on the black hole spin, but it's only of the order of a few %, which means that if we are able to get black hole images and measure the size of this shadow, it would be a pretty powerful test of general relativity at these high curvature scales. So let me dive right into the theoretical tools that we have developed over about 20 years to study black hole environments, particularly that scale at which I said the accretion disk forms from a feeding radius down to the horizon. The bread and butter tool in my field is GRMHD, and even though I'm going to try and avoid acronyms, this is so common that I thought I would introduce it to you. General relativistic magnetohydrodynamics. Typically solve it in Kerr spacetimes, although recently we have been able to extend that to non-Kerr spacetimes as well. And it looks like this. You set up some initial conditions. There's a feeding torus that tries to mimic gas coming in from large distances. It is in hydrostatic equilibrium. We thread it by some initial weak magnetic field, and we just let the whole system run and develop into an accretion flow. So this is from my own group, but there are literally tens of groups that work on this. As you can see, an accretion disk forms, and there is angular momentum transport. Fields grow through a process called the magnetorotational instability, and that just shapes many processes that happen within the black hole accretion. This is quite useful, and the reason is that it allows us to explore a variety of initial conditions and parameters around black holes. For example, we can change the black hole spin, the mass accretion rate. We can play with particle heating in the plasma. I will come back to this at the very end of the talk, why that's important and how we can do better. And they're expensive simulations, so we typically use large-scale computing resources to run this to steady state and explore the parameter space. From that to observables, there is usually another step, that is general relativistic radiative transfer. So we take volumes like this that are snapshots in those GRMHD simulations, where we have density, magnetic field temperature, etc. And we look at the emission and absorption processes in that volume, and we trace it again through geodesics to an observer at infinity. This is our image plane, and you see that we get images that are more realistic than that flashlight that I showed you in the beginning. It has the same features, but now we're asking ourselves, what is the source of the photons that actually light up the black hole, and what does it look like an observer at infinity? So I will show you a collection of these two steps put together that we did within the EHT collaboration. And I will point out a few common characteristics. So this is that parameter exploration that I told you about. Change mass accretion rate, change black hole spin, change observer's inclination. Are we near the equator or the pole of the black hole? And this is just a library that we put together with my former student, Leah Medeiros. And as you can see, there are thicker rings, there are thinner rings, there are crescent-shaped ones where we see closer to the equator, and the Doppler effect makes one side of the image brighter than the other. And there are full ring ones, like the one that you see here. But uniformly, what we see is that there is indeed that bright ring that surrounds that blackness, that shadow at the center. So through studies like this, we can quantify our expectations for the image size and the shadow size, as I will tell you in a little bit. These types of studies, albeit not as sophisticated as the ones that I showed you, we've been doing since about the late 90s. They weren't these large scales of GRMHD simulations, but they had pretty much all the characteristics that we needed to understand what will it take to image black holes. And one of the things that we did back then is determining the optimal wavelength at which we can see all the way down to the horizon and do the studies that I'm going to tell you about with the images. Why is this important? Well, this is mostly synchrotron emission. If you look at a longer wavelength, like a centimeter, what you will see is the emission from optically thick torus. So this is opaque to radiation at that wavelength, so you can't see down to the horizon. Let's change that wavelength and see what happens. By the time you reach a millimeter, you're here. So there is sufficient light generated around the black hole to light up the horizon, but it is not so little that your telescopes can't see it. So there is this optimal wavelength that the studies early on that actually I led helped determine. And this is a series of two papers back in the year 2000 and year 2001, when we were thinking about imaging black holes for the first time down to their horizons. And we considered two different techniques, both interferometric imaging, but one in the millimeter wavelengths. In this paper, we showed that it will take about a millimeter of wavelength of light to get down to the horizon. And there were already some interferometric imaging efforts or size determination efforts. As you can see in the late 90s, we said, based on our models, we will be able to hit the horizon at 1 millimeter. At the time, there was also a space interferometer concept in the X-rays as part of the Beyond Einstein program. Some of you might remember that got canceled later on. So we also looked at it and identified two targets that we could reach with either an X-ray telescope or a millimeter wavelength interferometer and get down to the horizon scale. So that's where we identified the black hole at the center of our own galaxy, Sagittarius A star, as well as the black hole at the center of the M87 galaxy as the prime targets. So we had prime targets based on our theoretical modeling. We had the optimal wavelength, and the next 15 or so years, we spent building the collaboration and the telescope array. Now, the angular size, when I say optimal targets, obviously, this is a bit of a stretch because even the best two targets in the sky are 50 microarc seconds across, the expected size of their shadows, or 10 to the minus 6 degrees. Obviously, a single telescope, no matter where you put it, is not going to be able to resolve that. That's why, as I mentioned, these were already interferometric efforts that started, and this was the space interferometer concept. So this is the Event Horizon Telescope in 2018. Since then, we have added 2 more telescopes to the array. And as you can see, it truly took a global-sized array to be able to finally do this experiment. Stations range from the Greenland telescope near the North Pole to the South Pole telescope, Hawaii, Arizona, Mexico, etc. So this was a global effort between that 2000 paper that I showed you in 2017, when we took the first array size data, the array grew like I showed you here. I want to take just a couple of minutes to talk about the data before going back to the theoretical modeling, because I think it's important to understand the nature of the data to be able to, first of all, understand how the modeling works, and second, to understand how to make it better. So this is a typical bare long baseline interferometer geometry, where you put telescopes at different parts of the Earth, record the signal coming in. The atmosphere introduces noise. There are hydrogen maser clocks that time tag every incoming wave at each of these telescopes. Of course, there's a time delay between when the signal arrives here and a signal arrives here. You write quite literally petabytes of data. You take those hard drives, take them to a correlator, which is fancy high-performance computer, and you correlate those signals. You literally multiply them, find that time delay between the two, and find when the common signal that you can describe between the two. So why does this work? Well, basically, if you had only 2 telescopes and one point in time where you took a snapshot, that would give you a single Fourier frequency, spatial Fourier frequency, that is aligned with the direction of the projection of these telescopes to the sky. So in the Fourier space, let's just put this. Let's say that this is the distance L between the 2 telescopes. It would give you a single point. This is just the mirror symmetric of that. That is that separation between the telescopes divided by the wavelength. This is the east-west spatial frequency, north-south spatial frequency. And it just, each telescope pair will give you that one measurement. That's not an image. That is just one Fourier frequency. To make an image, you have to more or less fill that space. How do you do that? Well, you rely on the rotation of the Earth to get a different look at the source as the Earth rotates. That's why there are these tracks of points for each telescope pair. And then, of course, as new telescopes come into view with the Earth's rotation, that gives you another pair which slowly fills the Fourier space. And when I say fills, that's an overstatement. This is a very sparse Fourier coverage. When we did this in 2017, there are 2 targets, M87. Here now it's color-coded with telescope pairs. This was our coverage for M87. And let me just flash it and then I'll come back. This was our coverage for Sagittarius A star. Now, there can, of course, be azimuthal variations in the image. Ultimately, we want to reconstruct a 2-dimensional image. But for the sake of the argument, let's just say we don't care about azimuthal variations. Let's collect all of this into a single plot where you look at the amplitude measured at each of these locations in the UV plane, the Fourier amplitude, as a function of the separation between the the two telescopes, so the baseline length. And what you see is that there is a very characteristic structure of a compact image that is a Bessel function in the Fourier space. Not only that, but Sagittarius star looks the same. Okay, so just by looking at this, you already know that you have a compact image that has the telltale Bessel function structure. This is what we call the zero baseline flux, zero the separation, first minimum, second minimum, and then the signal to noise gets bad. The first minimum, I'm going to claim and then show you, in the visibility amplitude, already gives you the image size. So just by looking at this, knowing something about Fourier transform of compact images, we can tell that this is about 52 microarc seconds because the baseline, that minimum, first minimum, occurs at a baseline of about 3 gigalambda. Okay? Why is that? Well, let's now take, again, M87 data, not color-coded anymore, and play around. I said compact image. Compact image means sharp edges. We can start with a disk, right? A disk has has sharp edges. And for reference, this is the 50 microarc second scale. The Fourier transform of this image here is this green line. Anybody can see that that's a terrible fit to the data, right? Okay, what can I do? I can change the image size. As promised, I had to make it about 52 microarc seconds, get that first minimum right, but at the cost of getting the rest of the function wrong. What else can I do? Well, it turns out the only other thing I can do is turn it into a ring as opposed to a disk. Okay? So this is why we were sure the minute we saw the data that there was a hole in the middle, that it was about the right size, and that there was a hole in the middle. So we knew, even without analyzing the data thoroughly, that the experiment had more or less succeeded. So why is this still off a little bit? It's because this is corresponding to infinite resolution. It's degraded to the finite resolution that's set by the diameter of the Earth between our telescopes. And that's that last bit of correction. So you're like, okay, we're done. We can go home. Oh, we did a lot more. We lost so many nights of sleep for several years trying to get two-dimensional images and physics constraints and understanding how the black hole environment actually works. One of the things that we did early on is called a regularized maximum likelihood method. You take an image plane, you pixelize it, and you assign arbitrary brightness to each of those pixels. And then again, this is the data that we're trying to fit. So let's have a trial function with this thing right here. And you again define a chi-squared. The typical chi-squared is right here. But because you have so many more points in your pixel, the n-squared pixels, and data points here, there is no unique solution. So you impose a penalty called a regularizer. In computer vision, there are some physical regularizers, for example, smoothness of the image, etc. In black hole images, there are very few physically motivated regularizers that you can impose. There are sharp edges. In fact, I was telling you there is a point that brightness comes to a very sudden end. There are filamentary structures, etc. So we don't have motivated regularizers. So what we did was try a lot of different regularizers and weights. I'll just show you one minimization process. But as you can see, what is being plotted here is the north-south and east-west cross sections of this image. This is the east-west, this is the north-south, and this is the best fit image with this set of regularizers. So this is what we did early on. Putting it together, Sagittarius A star on the left, slightly bigger in angular size, an 87 on the right, a few image elements that are immediately obvious, the central brightness depression that we are associating with the black hole shadow. There's a narrow ring of emission from surrounding plasma, as we expected, and there's a north-south asymmetry, more visible in the M87 image. A little problematic that it's not fully there in the Sag A star image, coming from the rotation of the gas. And in fact, M87 has a jet that is in this direction, such that the brightness at the lower part of the image is aligned with our expectation of the rotation of the gas. Okay. So from here onward, I'm going to touch on 3 small different topics. Again, coming back to theoretical modeling of black hole environments. The first one is going to be, now what? Pretty pictures, fine, the experiment succeeded, millimeter wavelength worked, et cetera, What did we learn in terms of physics? The second part is, now that you've done all of this theoretical modeling, you do something better than the regularized maximum likelihood that I just showed you. The third part is, now that you've done all of this theoretical modeling, are you satisfied? Are we okay? Do we understand the plasma? Can we go home? So if time permits, I'm going to get to all 3. If not, I can always talk to you offline. One of the things we did in our theoretical modeling efforts, as I mentioned, is go beyond the Kerr metric. Reason is that if you want to test the predictions of a theory, you need to see whether the predictions of some other theory are different. And luckily, what we found out when we did these non-Kerr models is that indeed, apart from the case of the boson stars, there's always a shadow surrounded by a ring. This is the Kerr that I already showed you. This is analytic Johansson-Psaltis, parametric deviation, or SEN, wormhole, photon, etc. Good thing is, when the metric is not Kerr, these features are still there, but the size is different. So by changing the metric parameters, you change the size of the shadow and you change the size of the ring, but they change in tandem. And that's good. That gives you a key distinguishing characteristics of different gravity models in measuring the size. And it's also good because what you have observational access to is just the bright ring. So what you're trying to infer is the size of the shadow. That's the gravitational signature. So you need to calibrate. You need to define factor, that is the diameter of the image over the diameter of the shadow. And the great news from all our explorations within Kerr and outside of Kerr is that this relationship turned out to be quite tight. So for each image, we said, let's do to it what we do to real data. So Mach observed every theoretical model and said, what ring diameter would I measure? And we said, what is the shadow size for this theory with these parameters? And we did that for each one of these models. And this is a histogram that shows you the combined effort. Actually, this is work that I led and my group at the time in Arizona worked on. And you can see when I say the relationship is tight, there's of course a spread, but this fractional diameter difference, alpha minus 1, peaks at about 0.1 with some uncertainty. That's great. This is our uncertainty. This is our theoretical uncertainty. We can take it and turn it into a measurement uncertainty, which is exactly what we did. For Sag A star, the measurement worked particularly well because we already had very tight constraints on the expected angular size from the mass of the black hole. And why did we have that? Because Nobel Prize a few years ago, the stellar orbits around the galactic center, followed by two groups for over 20 years, Kepler's law, clean problem, that gives you the angular size of the black hole. So that's this measurement right here with its own uncertainties. This is 6 square root of 3 that I already showed you in the beginning, the shadow size for a Kerr black hole. This is that parameter alpha that I showed you in the previous slide with its own uncertainty in terms of ring to shadow diameter size. And this is a deviation from GR parameter. So if delta is not 0, this is the measured from Sag A star. This is all of the other measurements and calibrations. Then we would say this is not what we expect from general relativity. As you can see here, the delta peaks around 0. There's a finite band here that comes from the unknown spin of the black hole, that percent correction that I had mentioned. And these are different algorithms by which we reconstructed it. But all of these, as you can see, point to what we expected for the image of that black hole. So we'll keep looking. We are hoping that black holes might be one environment where if there are deviations from gravity, there might be some signature showing up. Obviously, we're also looking at cosmological scales where we have to talk about dark matter and dark energy. But so far, we are not seeing any deviations from dark. So second part is, okay, now we have all of this simulation library. Do we still have to do that pixel-based regularized maximum likelihood? Or are there better ways of maybe learning about the image using those? So this is a classical machine learning technique. In fact, it's just dictionary learning that we did, again, in my group. Just to remind you, reconstructing sparse images, these are all the different regularizer choices that we had to do. And then we subgrouped them, etc. And we averaged over them, which meant that the final image did not actually get down to the resolution that the array was able to give to us. It was really dominated by Gaussian filters and the unknown regularizers, etc. So the fuzzy donut, unfortunately, as it was called in some outlets, was partly because of our image reconstruction algorithm. What can we do better? Well, we can turn to a tried and true method called principal component analysis. So we developed this for interferometric imaging and modeling that we called PRIMO. I showed you already the many, many thousands of simulated images. So what can we do? Well, instead of working in the image domain, where we have to pixelize and deal with all of that, we actually have methods in which we can fit the data directly in the Fourier domain. And not only that, but we can also use a basis that is more appropriate for reconstructing black hole images. Just like we use Bessel functions sometimes. And like we choose a basis set that is more appropriate for the problem that we have. Effectively, the machine learning part of this is that we didn't predetermine an analytic function to use to reconstruct the images. We let the machine tell us what that basis set is. So how does that work? You take all of this, and what the principal component analysis gives you an orthogonal eigenbasis for the space of images. Right, so this is all the models that you're learning from, and this eigenbasis allows you to reconstruct many types of images that have holes in the middle of different sizes or no holes even, and different azimuthal asymmetries. So it just turns out to be a much better basis set, a much better dictionary that you can use directly in the Fourier domain to reconstruct. So when you make this eigenbasis, this is the example snapshot that is not part of this original simulated images. This is filtered to HD resolution. And then you can ask yourself, from this new basis set, how many do I need to reconstruct a high fidelity image? So we tried, sorry, I went too fast. With V components, you can see that you're already getting the brightness kind of right, but none of the fine scale structure. So let's go to a higher number of components. With 20 components, we're now getting the, this would be the ideal case of having all the information about the image and the resolution of the EHT. And this is what you're able to reconstruct with 20 PCA components. So it really reduces your degrees of freedom. It is a much better eigenset for reconstructing images. And you've learned it from a library of images that you generated. You've never proven completeness, but it turns out to be a nearly complete set in the sense that you can use this basis to reconstruct any compact image that we have tried. You're not baking anything in. That was one of the questions that we got. Are you not baking in something about what you expect from simulations if you use them to reconstruct images? No, it's just a smart basis set. And you're not limited to what went into the simulations. Okay, so we decided to truncate it at 20 components. And the reason this works is that I showed you already in the data that Bessel function has a particular ringing wavelength that comes from the size of the image. So even with a sparse coverage, what this is telling you is that because Primo learns the correlations, even if you have data only here, it's actually able to constrain the function within this correlation length here. Same thing here. If you have data in this part of the parameter space, it is able to constrain within that correlation length what the function is doing. So basically, it says, what is the minimum sampling you need to do of a interferometric image in order to get all of the information out? So this is the explained part of why this method works. With that, we were able to take the original reconstruction of the M87 image in 2019. And this is not limited to EHT resolution. So this is just raw reconstruction. But of course, we don't have that fine scale information. That would be extrapolation. We don't trust that. We're just learning within the correlation lengths where we have data. And at the EHT resolution, this is what that image looks like. So as you can see, you have a lot finer features than our original RML methods. Okay, I have a little bit more time, so I'll spend the last 5-ish minutes on, I advertised HT models to you. I said we used it in all of these different ways. We did physics tests, we did better imaging algorithms. Am I saying that the models are adequate and complete? Far from that. In fact, there is a lot of missing physics in those models. You're not getting anywhere near the kinetic scales where dissipation processes happen, as I will explain to you. And one of the ways in which we know you're not doing extremely well is by looking at the variability of the total source flux. So forget the details of the image, integrate over all of it. How bright is my source? Because of the turbulence in the accretion disk, it's expected to change on some time scales. This is what we predicted from all of those models. This is the flux in Janskis, time scales in hours, that the source would vary all the time by quite a bit, going from 3.5 Janskis to 1.5 Janskis. Okay? That's not what we saw. In fact, we were worried based on our theoretical models that you wouldn't be able to reconstruct a robust image if the source keeps changing while we're looking at it. Instead, what we saw was a source over a 5-day period, so longer than this, changing not by much. As you can see, there is a little bit of variation up and down. We saw a flare here, so that's a whole other type of physics, non-thermal event happening. Even after that, it recovered to about the same flux. So if you looked at the mean variability, RMS variability in the real data, and plotted it on top of this, it would look like the green band. So our models are too variable. That's actually not super surprising, because one thing we get right is the overall dynamics of the flow. But from that to the thermodynamics of the flow to the images and fluxes, we're making quite a few assumptions about what is happening to the particles in the flow. So this is just one diagnostic that already shows you our models are not complete. Parenthetically, we also lack the physics that reproduces the flares, but that's another topic. So to explain to you what we are able to do and what we should be doing, I'm going to use this this plot where it's the wave number k on the x-axis and the turbulent power on the y-axis. But let's forget about the turbulent power for a second. This is the GRMHD scales where we simulate the entire disk. There's a type of simulation called a shearing box, where you take a small piece of the disk, and because in the overall disk there is shear, there's Keplerian shear or maybe even non-Keplerian shear, you put those as boundary conditions. It allows you to study processes that at a slightly higher resolution, maybe 3 orders of magnitude better resolution. But still, from that to the scales, like the ion or the electron gyroradius, where the energy in the accretion flow gets pumped into either the ions or the electrons and heats them, and therefore sets the thermodynamics of the flow, is yet another 9 orders of magnitude. This was already a theme in our cosmic ray workshop earlier this week. In plasmas, it's really difficult to simultaneously simulate large scale and the kinetic scale where interesting things happen. So luckily for us, there is one type of heating mechanism, which is probably the dominant heating mechanism, that has an inertial range of cascade. What do I mean by that? So at the GRMHD or the accretion disk scales, I mentioned that the magnetorotational instability is thought to drive the turbulence. What that does is pumps energy into both slow waves in the plasma and alphane waves in the plasma. Throughout this range, we are largely decoupled. So there's a cascade of power in both the slow waves and the alphane waves to small scales, to large K, that doesn't really talk to one another. So if you're able to understand how energy is partitioned at these large scales into these two modes, and then they come down, and slow waves are primarily heat the ions, and alphane waves heat both of them, but primarily the electrons. And at least you have some beginning guess as far as what your electron temperature should be, as opposed to really we don't have any idea. We're going to try all sorts of things in our modeling. So this is what we've been doing recently, exploring this channel of heating to understand the ion and electron temperatures a little bit better than the guesswork that we've been doing so far. And in particular, we've been using local shearing box simulations to understand this partition and how that translates into electron and ion temperatures. This is based partially on the work on Kawazura and collaborators a few years back, where they showed that the heating that goes into the electrons over the total heating, the dependence on the plasma beta. That's something that I kind of swept under the rug. It depends, of course, on what they called compressive over alphane, but it should really be slow over alphane. It has a pretty significant dependence on its power ratio, and also on the how magnetized basically your plasma is, or the magnetic energy to the thermal energy. That's your plasma beta on the x-axis. So if we know slow to alphane power ratio, and we know the local plasma beta, then we have a pretty good sense of where we might be on these curves as far as how much of the heat the electrons get, at least through this heating channel. So as I mentioned, we've done a broad range of shearing box simulations with different plasma betas, Keplerian and non-Keplerian shear. And as you can see, there is a dependence on the shear rate of the slow to alphane power ratios, and there is a weak dependence on the plasma beta of this quantity. So we've been able to 1.5 is the Keplerian shear that you see with a star there. And with this shearing rate, we were then able to calculate these heating ratios, and not just the heating ratios, but there's also compression, there's cooling, etc. in the system. There are Coulomb collisions. So ultimately, it is this heating ratio and what is the final ion to electron ratio. And we highlighted the Keplerian shear of 1.5 here. So in GRMHD simulations, we are typically within this gray band here. And that already sets us into, allows us to set limits for this temperature ratio that we have not been able to set before. We are literally exploring 2 orders of magnitude in our empirical simulations, as opposed to here we can say, okay, let's look at the local plasma beta and figure out as a function of the shear rate where we might be in the temperature ratios. So takeaways that I want to leave you with, GRMHD models, just by virtue of being basically mass, momentum, and energy conservation, and some description for angular momentum transport in the disk, that's the main features right. They've been extremely helpful in terms of getting the basics. They do not capture the dissipative processes happening at smaller scales, and studies of electron heating are at least one step towards more predictive models of the thermodynamics that will translate into better observable predictions. And it may be able to fix the variability problem. We haven't looked at it yet. So let me put up the conclusions from the whole talk. I hopefully convinced you that we saw the telltale sign of a black hole shadow in the images of both M87 and Sagittarius A star. The size is consistent. Our chagrin, the predictions of general relativity. The models have already allowed us to do better reconstruction algorithms through dictionary learning, PCA, and it's a very challenging problem to get the plasma right, as this audience will resonate with, unintended. And we are making some progress on that front as well. Thank you.
And so just for people have questions, please speak up. Your voice will be captured by the brain gate. So you're going to go up. So
Thanks for this wonderful talk. I have two questions. Number one, the GRMHT models assume the collision limit. Now, the part of the Milky Way is larger than the size that you have shown, so only we're not allowed to actually use GRMHT at all. Is it a surprise that they nevertheless produce the features right? Because it could be quite different, right? I mean, so you could have a lot of kinetic effects changing appearances.
Yeah, so it is true that the mean free paths, particular types of accretion flows that I talked about today, are not the bright quasars that we see at high redshift. They are gases trickling into them at slow rates, low mass accretion rates, and as a result of that, the density in the particle density is pretty low. So it's not really in the fluid limit where we can use GRMHT. Nevertheless, so as a result of that, for example, we see pressure anisotropies. That is a kinetic effect. But ultimately, what we are solving for, the mass, energy, and momentum conservation, even in the semi-analytic models and the GRMHT, and the presence of tangled magnetic fields, is allowing us to, yeah, I mean, is it surprising? It's a little bit surprising. There will probably be other dissipative effects that change these predictions, but ultimately, they work well enough. That's what I can say.
So the emission you're talking about is this thermal synchrotron radiation. So are you talking about processes that heat the electrons thermally and then they emit basically whatever distribution functions they have then into the radio? And then is this the correct assertion?
That is correct. So there is that intrinsic assumption in all of these that the electron distribution function as a result of whatever heating happens is a thermal distribution, and therefore the dominant emission mechanism at the millimeter wavelengths is thermal synchrotron. However, this is something we worried about all the way back in 2000, whether the image size would be affected by the presence of non-thermal electrons. This is literally something we've thought about 25 years ago. Hybrid here refers to a population that has a thermal and a non-thermal electron distribution. So electron distribution basically has a Maxwellian, but it also has a non-thermal tail through whatever other acceleration mechanisms, not just the heating mechanisms. And as you can see, the largest effect is at the smaller frequencies, longer wavelengths, where the image size significantly changes. By the time you're near the horizon, there are transient effects like flares that happen. Overall, the morphology of the image is terribly affected.
Scientists claim that Fermi bubbles in our Milky Way Galaxy are lasered by a supermassive black hole, specifically by the jets, as opposed to galactic winds. The orientation of the jets is obviously related to the spin of the black hole. So I'm wondering if the orientation of the jets that you can hopefully infer from these imaging studies are consistent with the orientation of the jets and morphology of the bubble.
That's a very good question, and I completely forgot to mention this when I did the Sagittarius star and M87 comparison. So thank you for bringing it up, Mateusz. M87, the reason we know that there is a black hole there, or we suspect that there's a black hole there for many, many decades, is this beautiful prominent jet that's the size of the scale of the galaxy. And you can see it at pretty much any wavelength that you observe it in. It is prominent. For Sagittarius A star, we've never seen a jet. We've done studies, again, at many different wavelengths, obviously not at the resolution that the EHT did before, but it does not appear to have a jet. Whether that's a difference in the spin of the black hole, whether that's difference in the energetics of the flow, we don't know. But jet, no jet. So Fermi bubbles by this quiescent little fella? Maybe. I don't know. It doesn't have a jet that we see.
I've got two questions. One is that, can you Primo method help to identify the polarization image? And another question is that, do you have any comments on the polarization image we obtained recently?
Can you repeat your first question, please?
Yeah, you mentioned your eigenvalue decomposition method. And can you extend this method in the polarization image, because there is a higher dimension image?
Yes. Another topic that I didn't touch on is polarized images. Everything that I showed you is total intensity. But with the EHT, we are able to observe in two polarizations. So in subsequent studies, or at least like one avenue of research, we've looked at the patterns of polarized light and what that says about how ordered the magnetic fields are around the black hole and how that translates into synchrotron radiation, etc. Absolutely, Primo can be extended to polarized images. We would just need to use the image library that we produce from polarized radiative transfer as opposed to total intensity that I was showing you. And in fact, one of our efforts right now is multi-frequency now, because EHT started observing another wave band. So yes, it's readily extendable to both of them. We've learned a lot from polarized images. I just didn't have a chance to talk about it, primarily how ordered the magnetic fields are in the vicinity of the black hole.
I noticed from the location of where the EHT telescopes are that there's nothing in Australia or South Africa or elsewhere. Is that because he doesn't help much, or just a sociological thing?
Sometimes it's just the availability of, so we did not build the dishes in these places. We put the millimeter receivers and the recorders and the hydrogen masers and basically added them to array. Two requirements for this observing wavelength is dry. Millimeter wavelength suffers terribly from moisture column in the atmosphere. It's high, again, for the same reason, both atmospheric turbulence, the coherence length is, coherence time is short, so it introduces additional complications in the image. There is a telescope being built in Namibia. Right now, it's one of the few that we're actually building the telescope through new funds, as well as the receiver. I don't know of plans for Australia, probably because the altitude requirements, but we can look at it.
Yeah, I was pleased to pick up. I was wondering about the mentioned question about the relativity that I think and I'm eating what might be actually well the HD. But when it comes to things like decompose it, studying how the MRI drives slow mo update when a bit longer, I would be the intuition would be that there the research might be a bit less size and that's probably not.
We are working, so the coupled cascades are seen in the reduced MHD. So what we're doing there is basically saying that at the shearing box scale, that we can still apply MHD and look at excitation of waves. Am I worried about it? I mean, at the same level as whether any of these kinetic processes happening at the small scale changes the overall dynamics of the flow. There is one mostly kinetic simulation that found pretty similar by Kunz et al. That found pretty similar results to what we see in MHD, but it needs to be seen, I think. Scale separation is a real problem.
Yeah, I could ask you a very naive, experimental question. So first of all, thank you for making your talk accessible to those who know nothing about black holes. If you want to learn more, I understand that kind of part of the idea is to constrain the parameter space of the model. To get there, do you assume that if we looked at an infinite number of black holes, you would cover all the phase space? Or are you, like, is every black hole sufficiently different? Would it help to study more black holes, or would it help to study those black holes better? Like, what's the way to constrain?
Yeah, thank you for that question. I do think we need to study more black holes. The reason is that we don't fully understand. For example, black hole spin could be different between different black holes. We can model it, but we haven't seen in action. For example, is it coupled to presence of jets, not presence of jets, or is it something entirely different about how magnetized the flow is, or something different that we haven't really been able to pin down? We have a single line of sight to every black hole. So even though almost everything that I showed you, apart from this Doppler asymmetry, like you would still see the hole, you would still see the donut, but would the image look somewhat different if our line of sight is different? Is the thermodynamics happening a little differently because the collisional time scale is different compared to the accretion time scale? We absolutely would benefit from looking at more black holes in terms of characterizing their accretion flows there, and especially at the scale of the horizons. That requires going to space, and we are working on a couple of concepts. There is at least one concept that would make about 30 more black holes accessible to us at the horizon scale, but it's a huge undertaking.
Two more questions up the back.
So follow up to Matusha's question. Like, were such curious as to launch a jet or jets? Can you say which direction they would be launched in? Is there any constraint?
Yeah. We are about to submit a paper about the lack of asymmetry, the large-scale asymmetry in the image of Sagittarius A star. The easiest thing to say is, well, maybe we're looking at its pole-on. But we're already looking at M87 at about 17 degrees from the pole. Say the same thing, in fact, more stringent, less than 10 degrees for Sag A star is a little bit nauseating. And the other thing that helps is if the angular velocity is subkeplerian. Of course, the size of this asymmetry, this Doppler boost, is going to depend on the magnitude of the azimuthal velocity. So we are also looking at processes that make the angular velocity profile different than Keplerian. So having said all of that, if you just looked at it with blinders and said, how can I make this image compatible with with lack of Doppler asymmetry, you would have to conclude that you're looking at it near the pole. And if the jets are aligned with spin axis of the black hole, then the jet would come straight at us. But there are so many ifs in that statement that like you should just basically wave your hand and, you know.
Last one.
Could I just add a comment? I was wondering if those blobs could also be because Sagittarius A star, as you said, is very, very quiet. And M87 is not only more active, so accretion runs steadier on the right than on the left. So could that be linked to your variability? Because you use a long time scale in order to get the image. So it's sporadic, and sometimes in Sagittarius A star, it would more on that side active and more on this side. Could that help?
Thank you for that question. So there are two parts to the answer. One is 87 is a 6 billion solar mass black hole. Sagittarius A star is a 4 million solar mass black hole. Dynamical time scale near the horizon is different by the factor of the masses. So it is minutes to hours for Sagittarius A star, and it's days to week for M87. So during our observational span of nearly 10 days, it's okay to assume that M87 sits quietly. It's less okay to assume that Sag A star sits quietly. That's partially why we published M87 first and then Sagittarius A star, because we were worried about this timescale issue. In the data, it did not do that, though. It was actually, of course, it was bubbling along, like that we did see some change in the overall flux, but at the level that I showed you, and definitely not at the level that our models predicted. The second part of the answer is, what are these blobs here? They're mostly artifacts of our imaging algorithm. So in an accretion flow, based on the models that I showed you, there are flux tubes forming, there are density enhancements. So in principle, we could see bright spots that are short-lived, that are orbiting the black hole. In the collaboration, there isn't an agreement, but if you're asking me, these spots, the location and the appearance of those spots depend very strongly on the regularizers used. They move around, they align with the axes where we have more data. I think they're artifacts. So I'm not going to spend any time analyzing them.
Great. Well, we can continue the conversation at the wine and cheese.
All right.
Thank you so much, Feryal.
Thank you.